Thank you very much for the introduction. So we can view this talk as unconditional lower bounds on the running times of specific algorithms and of classes of algorithms. So first we'll look at one problem, max2CSP, and one specific algorithm for it. And I will try to convince you that the existing analysis on the upper bound of its running time is tight. And I believe that this lower bound even generalizes to broader classes of algorithms for this problem. Then I will talk about enumeration problems. So a bunch of algorithms are based on the enumeration of some subsets. And if the number of such subsets is at least some function of n, then of course your running time will be lower bounded by this as well. Let's start with max2CSP. So the input is a graph G and a bunch of score functions. Now the output will be an assignment which is an assignment of values 0 or 1 to the vertices of the graph with maximum score. Now what are the scores? So we have a nidic score, which is basically just a constant that is there for bookkeeping, but you might as well ignore it. It's not very important. You have a score for each vertex and for each edge. So a vertex gets a score depending on the assignment you give it. So if you assign the value 0 to a vertex, you get some score, which is an integer. If you assign the value 1 to the vertex, you get a different score, which is an integer as well. We also have scores on edges, and the score of an edge depends on the assignment to its endpoints. So there's 4 possible scores for an edge and 2 possible scores for a vertex. Now, we just want to find an assignment to the vertices that maximizes the sum of all the scores you obtain here. For example, this problem generalizes maximum independent set, max cut, max2 set, and some other problems. And instead of having an integer here, you could have formal variables, and in that case, you get polynomial CSPs. So your scores will then be formal polynomials. And you can do things like counting objects of size k. We'll stick with max2CSP. And we could also have a bigger domain, in which case you get maxd-CSP for domain size d. Everything I say still holds for polynomial CSPs with domain size d, but we will look at max2CSP only. So what is known about this problem? People have designed algorithms for this problem, and these are the current best upper bounds. So if you're allowed to use exponential space, there's Ryan Williams' algorithm, which runs in time 2 power matrix multiplication divided by 3 times n. And it uses exponential space. People have also looked at getting better running times for sparse instances. Now you measure the running time in terms of the number of edges in a graph. And here the best known algorithm has this running time, which basically just computes a tree decomposition and uses a bounded trivial space algorithm to compute the solution. So those 2 algorithms use exponential space. Now, people are also interested in polynomial space algorithms. Measured in terms of the number of vertices, nothing better than brute force is known. And measured in terms of number of edges, there was a 2 power 0.19 m time algorithm by Scott and Sorkin in 2007. And we will look at this algorithm in detail. It has recently improved to 2 power 0.18 m. So what I'll do now is I will present the algorithm by Scott and Sorkin. and design a lower bound for it as well that matches this upper bound. And this is quite rare, actually. So often in exponential time algorithms, we design an algorithm, we give an upper bound on its running time. But very often when we ask people to give you actually an instance that uses, where the algorithm uses this time, they can't come up with one. And usually you have upper bounds and lower bounds that do not match at all. Okay, so let's get to the algorithm by Scott and Sorkin. The first thing it does is it applies some simplification rules. So reduction rules for vertices of degree 0, 1, and 2. So if you have a vertex of degree 0 in your graph, well, you get some score for setting it to 1, you get some score for setting it to 0. Of course, you want to set it to the value that gives you the maximum score. Well, that's very, very easy. You just set it to the value that gives you the maximum score, and then you delete it from the graph. You update the niletic score function with this maximum. If you have a vertex of degree 1, so what can you do? Well, for every value of its neighbor, you can check what score do I get for this vertex and for the edge that maximizes basically the values. Oh, well, for which values do I maximize the sum of the vertex, sum of the scores of the vertex and the edge? So we do this for every value of the neighbor, and this allows us basically to integrate this vertex v and its edge into the score function of its neighbor. So this is very easy, and it can also be done for vertices of degree 2. Now, for every assignment to the neighbors of v, we can check how do I optimally need to set v so as to maximize the sum of the scores of this edge, v, and that other edge. And then I can again integrate all of this into one edge on the two neighbors of v. Now I can remove v and its incident edges. Okay, so we can easily deal with vertices of degree at most 2. Now, if every vertex has degree at least 3, we just do a very simple branching. So we select a vertex with maximum degree, and this algorithm prefers to select one with maximum degree that has a neighbor that has degree less than the maximum degree. Now it does a simple branching, setting this vertex to 0 or to 1. And then recursively solving the two instances that you obtain. Okay, so this algorithm is very simple, but it is quite hard to come up with better branching rules, in my opinion. Let's look at what happens for the degree 3 case. So suppose your input graph has maximum degree 3. So by using the simplification rules, we'll get maximum degree 3 and minimum degree 3. So your graph will be 3 regular. So what does the algorithm do then? Well, it selects a vertex, and it sets it to 0 or 1, and then what happens? So this vertex disappears. The neighbors become of degree 2. So the degree 2 reduction applies to them. So they're removed, and an edge is created in their neighborhood instead, if it wasn't present already. So in the worst case, how many edges get deleted? So we analyze the running time in terms of the number of edges now. So here we see that 9 edges get deleted, and 3 new edges can potentially appear. So the net effect is the removal of 6 edges in each of the 2 branches. And then since we remove 6 edges in each of the 2 branches, we get a running time of 2 power m divided by 6, where m is number of edges, for cubic instances. And then the analysis of Scott and Sorkin is a linear programming analysis. So it's basically equivalent to measure and conquer, where you assign a potential function to your instances and track the progress you make in terms of that potential function. So for measure and conquer, we usually optimize the weights of this potential function with a convex program. But since in this problem, basically the two instances we create are equal, or they have equal weight at least, so they have equal measure for this potential function, this convex program reduces to a linear program, actually. And so they did an LP analysis of this algorithm and deduced that if you can solve the cubic case in this time, then you can solve general max2 CSP in that time for this function beta of alpha. And then by applying this, they conclude that max2 CSP can be solved in time 2 power 0.19 m. So when I first saw this algorithm, I was quite happy to read it, but I was quite disappointed at the end because I had no idea how to improve it. And it just seemed impossible. They had done everything they should do, and yeah, I just gave up. So improving the analysis indeed seems very difficult. So the tight constraints in the analysis is, well, you have one tight constraint for degree 3, where basically the 6 edges disappear and nothing else happens. For branching on degree 4, the tight constraint is when neighbors have degrees 4, 4, 4, and 3. For branching on degree 5, the worst case is when the neighbors have degree 5, 5, 5, 5, and 4. So you might wonder, so why is it not the 5 5s? But the case where you need to select a vertex of degree 5 where all neighbors have degree 5 cannot occur too often. So actually it can occur only once unless you disconnect your graph, unless your graph has multiple connected components. So these are the worst case branchings in this analysis of Scott and Sorkin. And what we do is we actually construct instances where the algorithm only branches according to these 3 branchings. Well, it always either branches on a vertex of degree 3 where nothing else happens, or on a degree 4 vertex whose neighbors are like this, or on degree 5 where the neighbors are like this, and no additional simplifications happen. Moreover, we need to select these branchings in the right proportion to get actually this lower bound on the running time. So in the most general case, we have a 5 regular graph where the algorithm has to branch n by 8 times on degree 3 vertices, 3n divided by 20 times on degree 4 vertices, and n divided by 5 times on degree 5 vertices. Interestingly, this proportion of the branching cases comes out of the LP analysis. Actually, you can compute it from the dual of the LP. And this somehow leads me to believe that maybe for many other measure and conquer analysis, the current analysis might be tight, except that we didn't manage to design such instances where this running time occurs. Okay, so for degree 3 graphs, this is quite easy. So I have a 3 regular graph. I want that, well, what should happen to my instance? Well, exactly this. So 6 edges should disappear, and I should create 3 new edges. And this scheme should be applied over and over again. And this is the case for this graph. So we just have these subgraphs arranged in a cycle. Now, if we choose this red vertex here and branch on it, what happens? Well, the vertex disappears. We create a bunch of degree 2 vertices. They get simplified, and we replace all of this by an edge. And again, we have a quite similar graph, except that it's 4 vertices shorter. And here, again, the algorithm might select, again, one of these vertices. Since the algorithm doesn't specify which vertex to select, we can make it select this bad vertex. Note that if it selected this vertex, that would be much better for the algorithm because the whole instance would disappear. Okay, so but on this graph, now, depending on the decisions the algorithm makes, the running time is 2 to the n divided by 4, which is for cubic graphs 2 power m divided by 6. Now, for degree 4 graphs, what do we do? Well, we start from this construction for degree 3 graphs, select a perfect matching in that graph, delete it. We delete the edges of this perfect matching, and basically replace them by this construction here. Now, okay, on this graph has maximum degree 4. So the algorithm will select a degree 4 vertex, preferably with a neighbor of degree less than 4. For example, this red vertex here. So now it branches on this red vertex. What happens is that this vertex disappears, all its incident edges disappear. Now this path on degree 2 vertices appears, or well, this vertex will get degree 2. So it gets reduced away, and it basically creates this edge that we deleted before. The next vertex to branch on could then be this vertex, etc. So it branches on every second vertex in the top row, and after doing this, it leaves us with this lower bound construction for degree 3 graphs. For degree 5, we again rely on the previous 2 graphs for degree 3 and degree 4, but now the proportion must be somehow different. So note that here for the degree 4 construction, we really exhausted, we really added a maximum number of degree 4 vertices. But here, we shouldn't add as many degree 5 vertices as we can, because in the end, we need to be left with some graph where the algorithm will branch on degree 4s first, and then we need more degree 3 vertices to branch on. So what happens here is the algorithm will just branch on these middle vertices, and then what's left is this lower bound for degree 4 and this lower bound for degree 3 that are somehow connected in an appropriate way. So what you get in the end is lower bound graphs or instances where the algorithm of Scott and Sorkin will really use this much time. This shows then that their analysis was tight for degree 3, 4, and general instances. So, more generally, say that an algorithm is myopic if basically what it can do is go through all the vertices, look at the neighborhoods of this vertex, of each vertex, and decide on which vertex to branch on, choosing the best such vertex by characterizing the vertex just by a fixed ball radius around it. So, which means that we can only check local properties, but no global properties. So you could, for example, go through all the vertices and always remember the best one you encountered so far, always just checking a local ball around that vertex. So our conjecture is that actually this cubic lower bound also holds for myopic branching algorithms for cubic max2 that is based on the same reduction and simplification rules. So now what you can change is you select this vertex differently on which you branch. So I believe that this doesn't help. And I also believe that this doesn't help in general. So for general max2 CSP. And moreover, I believe that this is true for every myopic branching algorithm. Note that the conjectures become stronger and stronger. So now an obvious question is, okay, now if we don't restrict ourselves to myopic branching algorithms, can we do better by exploiting global properties? Yes, you can. So in polynomial space, we can exploit separators that are balanced and allow us to basically branch on the vertices in the separator and then exploit the fact that in the end we get disconnected components where we get a huge gain because we can solve them independently. So there's a recent algorithm where we applied this idea and we managed to get the measure and conquer analysis wide and adapt it to this kind of separators. So we get, in general, for general graphs, we get an improvement from 0.19 m to 0.18 m. The biggest improvement is for cubic instances, where we improve it from m divided by 6 to m divided by 7.5. Okay, so we already started to talk a bit about classes of algorithms using these myopic branching algorithms. But now I want to talk about enumeration algorithms, and specifically about algorithms that enumerate objects. Let me start with maximal independent sets. This is a well-studied class of objects. So it is known for a long time already that the maximum number of maximal independent sets in any graph of n vertices is upper and lower bounded by 3 to the power n divided by 3. The bounds that are given in literature are much more precise, but what I really care about is the exponential factor. So the lower bound examples are these graphs. So if you have a disjoint union of triangles, every maximal independent set contains one vertex from each triangle. And since there are n divided by 3 triangles, and we have 3 choices for each triangle, we have this bound. And then for, depending on the number of vertices, you get slightly different bounds. So the enumeration of maximal independent sets is used, for example, for 3 coloring. So this is Lawlor's 3 coloring algorithm. So we can assume that without loss of generality, one color class is a maximal independent set. Otherwise, take your coloring, recolor some vertices red, so as to make your red color class a maximal independent set. So now the algorithm can just go through all maximal independent sets of the graph and check whether, if you remove it, you get a bipartite graph. If so, return yes. Otherwise, return no. So the running time of this algorithm is 3 to the power of n thirds. And of course, you cannot do better, really. For this specific algorithm, you cannot do better because of this lower bound example, which is, of course, trivially 3 colorable. But this is a lower bound for the running time of the algorithm as well. So we can, and this idea for maximal independent sets has been used for many different problems. So there's a bunch of algorithms that rely on the enumeration of all maximal independent sets of a graph. And of course, the running time their running time is lower bounded by the enumeration of all these maximal independent sets. There's a bunch of other objects that we could look at besides maximal independent sets. For example, we could look at maximal by cliques, minimal feedback vertex sets. So I'll focus on minimal separators and on minimal hitting sets. So the green rows here are tight, so we have a matching lower bound to the upper bound. But for many other objects, we don't have matching lower bounds and upper bounds. For minimal separators, the bound previously was 3 to the n-thirds, but it has been improved very slightly. Okay, let's look at minimal hitting sets first. So this is an easy one. So we basically take the maximal independent set lower bound and generalize it to hypergraphs of larger rank. So we basically take 2k minus 1 vertices, build all hyper edges, all possible hyper edges of size k. Now, if we select k vertices, we hit all the sets, we hit all the hyper edges, but any fewer vertices miss at least one hyper edge. So in this way, we generalize these triangles to basically complete hypergraphs of larger rank and get this lower bound. Okay, this is a very easy one. Let's look at minimal separators. So what's a minimal separator? Well, first of all, if A and B are two vertices in a graph, then an AB separator is a set of vertices such that there's no path from A to B when you move these vertices, when you move the set. An AB separator is minimal if it's not properly contained in any other AB separator. And a vertex set is a minimal separator if it is a minimal separator, a minimal AB separator for some pair of vertices AB. So this might be a slightly unusual definition of minimality, and it makes that this set S1 is a minimal separator, whereas this superset S2 is also a minimal separator. Namely, S2 is a minimal AE separator, whereas S1 is not an AE separator. Okay, so what was known already is that the maximum number of minimal AB separators in any graph on n vertices is at least 3 to the n-thirds, and this can be seen by the following graph. Well, to separate A from B, you need to select one vertex from each of these rows. So there are 3 choices in each row, and this gives you 3 to the n-thirds. And this was thought for a long time to be possibly also the maximum you could get. To convince you that this is not a tight lower bound, I'll improve it first very slightly by an easy construction. So now suppose we have 126 such rows. So 126 is 9 choose 4. Here we have 9 vertices. Each of these vertices is connected to exactly 4 of these 9 vertices, such that no 2 of these vertices are connected to exactly the same ones. That's why we have n choose 4 rows here. Now look at all the separators that do not contain any vertex from the first row. Then, well, they must contain the 4 vertices that this vertex is adjacent to in this column. Okay, so for the remaining rows, well, they still have some neighbor in here, all of them, and we have 3 choices for each of them. So the remaining rows, that's 125, so 3 choices for 125 rows, and that was excluding every vertex from the first row. Now, the first row is not special, so we could select any row to exclude all the vertices from that row. There's 126 rows. And this is the number of vertices in this graph, which has constant size. But now we make copies of this graph and merge the copies of A and of B. Now, it's easy to see that 126 is more than 81, and that's why this lower bound is larger than the previous one. We can push this further to a larger bound. And the current best upper bound is this. We just simplified the proof a little bit, and let me conclude. So the running time of the Scott and Sorkin algorithm for max2 is tight. And this leads me to believe that many other measure and conquer analyses might be tight as well. So for the number of extremal vertex sets in graphs, there's been a renewed interest over the last 6-7 years. It's motivated by exponential time algorithms. And you could discuss, of course, how much space these use and what's the delay of the corresponding enumeration algorithms. Okay, that's all.